Everyone, welcome to December's First Friday. This is LRFD Bridge Design with Zeyn Uzman. This is Ariana speaking, and I just want to thank everyone for dealing with the complications we had earlier today regarding emails and links. I appreciate your guys' patience, and as always, if you have any questions or concerns, you can send me an email at ariana@frontlineco.com, or you can give us a call at the ISPE office. If you look at the handouts section at the bottom, the handouts for this presentation are posted, and the quiz is posted on the First Friday Quizzes webpage. It should be in the link of the email that you eventually received with all of the instructions on it. If you have any questions for the presenter, you can type them in the questions or the chat boxes, and we'll talk about those at the end of the presentation. So without further ado, I'll turn things over to Zeyn. And yeah, there you go, Zeyn.
Hey, thank you, Ariane. Hello, everybody. Welcome to December 1st. I can't believe it's December 1st already. Giving a pinch hitting here, from what I understand, for somebody that couldn't make a presentation. So I'm going to talk about LRFD bridge design for timber structures. And this presentation is talking about a timber bridge that I built, or excuse me, did the design for a company that I do work for, York Bridge Concepts, and they're located in Florida. This project was a timber bridge in Port Charlotte, Florida, and the location is actually from one island to another. This is the third bridge that was at the location. The first bridge was a 7-span timber bridge, and these are all for light traffic. The heaviest traffic that these bridges see are essentially garbage trucks. Most of the residents travel on the island from one place to another via golf cart, but they also use their own personal vehicles to take a ferry that goes off the islands onto the mainland in Port Charlotte. Now, this bridge is replacing a 3-span concrete PPC deck beam bridge that had 2 lanes of traffic. And what the residents wanted was a 2-span bridge or 3-span bridge with 2 lanes of traffic and pedestrian usage. And so the island residents wanted to match the original structure, not the concrete structure. They liked the looks of it. York Bridge Concepts was hired to do the design and construct a new bridge. And during the process, we found out that there was county money being used for this, and so therefore we had to follow Florida DOT standards, which includes the LRFD design requirements. And the estimated cost of this bridge was about $3 million. Now, I've been working with York Bridge and a couple other timber bridge companies for coming close on 15 years. And primarily, we do everything service load design, because in timber design anymore, still everything is done service design. But because this had to follow Florida DOT standards, we had to do LRFD, and this was actually the first timber bridge that I did with LRFD design. And one of the things I found out on this is that it's grossly conservative to do things LRFD. And you'll see some of the beam sizes that we have once we start getting into this. Now, the design parameters use 2014 LRFD design specifications. The 3-span structure, 51-foot spans, 29-foot face-to-face rails with a 5-foot wide sidewalk on one side. Now, because of the environment being in essentially near the Gulf of Mexico, and actually you're within about 2 or 3 miles of the Gulf of Mexico, everything had to be concrete abutments and walls. And because people had to get from one side of the island, or one island to the other, we had to build a temporary structure next to the bridge, and that was a single lane bridge with traffic signals. this is an overall view of the bridge after it was built. You can see there's an island here on the right. There's an island here on the left. We had to fill in partially some of this approach work, and you can see the 1, 2, 3 spans. The temporary bridge went on the far side of it, and ironically, I mean, this temporary bridge was there for, I want to say, about 9 months and had no problems at all with traffic control at all. This is an elevation of the plan view of it, and you can see it's a timber railing, and the beams were glue laminated beams, and they're all 51-foot spans. And here's a cross section, and you can see here are the glue lams. It had a glue laminated deck with a wearing surface, a timber wearing surface put on top of it, and then the pedestrian portion of it is independent, and it is a two girder system with stringers and a regular timber decking. And you can see we have a concrete cap and we have concrete piles. So I'm going to go over the deck design, roadway girder design, pedestrian girder design, guardrail design, and a couple pictures of stuff that happened during construction. Now, this is a close-up view of what the vehicular part of it was. You had a glue lam beam here, a glue lam beam here, glue laminated decking, and like I said, a wearing surface. And all of the hardware used to anchor everything done with stainless steel because of the high salt environment. Now, LRFD design has different limit states and different load combinations that are used. And here is a photograph, or excuse me, a part out of the LRFD specifications that show all the different limit states. You have strength, service, fatigue, and extreme events. We primarily just designed everything for strength 1 design. Strength 2 applies for a special vehicle, which we didn't have. 3 and 4 and 5 are primarily for concrete and steel structures. And we didn't even, the only thing we looked at for service design, which I don't have covered here in the calculations, but service 1 is essentially deflection, and we didn't, we checked it, but it wasn't a problem at all. And here are the load factors for dead loads, and we're going to use the maximum DC for components and attachments of 1.25. So for the deck design, we're using planks that are 4 inches thick by 48 inches wide with a 2-inch wearing surface. And according to AASHTO, we distribute the wheel load over a width of 20 inches, but we're just going to do the design based on a 12-inch width of deck. And the wheel load is an HS20 truck, which is 16 kips, and the spacing between the glue lams is 2'3". Now, the interesting difference between timber design and steel or concrete bridges is there is no impact included in the design of timber structures. So that's one thing to keep in mind in the future for yourselves if you're ever doing a timber vehicular bridge. And when you get, so essentially you figure out what your dead loads are, your live loads. Your dead loads are, for timber, we use 45 pounds per cubic foot times the 2 inches. You get 8 pounds per lineal foot. The deck is 45 pounds per cubic foot times the decking is 4 inches. So you can see we get 24 pounds per lineal foot. We're going to use 25. And the wheel load is 16 divided by 1.66, which is the 20 inches. And that gives you 9.6 kips. Since this decking pretty much is continuous from the crown of the bridge to the ends, we're going to use a dead load moment of WL squared over 10, and you can see that we get a 12.7 pounds per foot moment. And the live load moment, again, is also, because it's it's continuous, PL over 6, so you're going to get 3,600 pounds per foot. So using strength design, you have your load combination is 1.25 times your dead load moment plus 1.75 times your live load moment, and that yields a moment of 63.16 foot-pounds, which, you know, is about what you would see on a highway bridge too if you were designing it with concrete or steel. And what you have to do is compare this to the allowable flexural strength, and your applied force or applied stress is the FU has got to be less than the phi factor times the nominal strength. And your nominal strength is the allowable stress from the NDS tables and AASHTO times these different factors for format, wet service, volume, flat usage, NC, depth factor, and then the time factor. The format conversion factor is what essentially converts your allowable stresses to LRFD stresses. And that's what I talk about here. Your volume factor is for a glue-lam beam. For horizontal laminated glue-lam beams with loads applied perpendicular, it shall be reduced given that below when the depth or width of the length of the glue-lam exceeds 12 inches, which is what we have here. The time factor, we're going to use strength 1, and so you use 80% of the actual load. So when you go through all of the factors that we have here, you can see your allowable stress for a glue laminated beam is 2,400 psi, but your nominal strength ends up being 3,840 psi, which is a substantial increase in your capacity. So we go ahead and we calculate out what our actual bending stress is, and you can see that your actual is 2370, which is substantially less than the 3840. Now the interesting note is if we were to design this working stress design, it would be much closer. These two numbers would be much closer. So the next thing I want to do is look at the stringer design on this one. They're 51-foot spans. They're spaced at 3 foot 1.5 inches. So, and we're going to use a glue laminated beam, which is 10.75 inches by 40.5 inches. Again, we're not going to use any impact. Go through again, you have your wearing surface, your deck, and now also your beam weight, and you end up, we're going to use 210 pounds per lineal foot. These beams are pretty hefty, and it's for a 51-foot span. And then your live load distribution, you still have your your wheel load of 16 kips, but we have a distribution factor of S divided by 10 because we have 2 lanes. So our distribution factor comes to be 0.31. Now this is simple span because the beams are not continuous. We have 3 51-foot simple spans. So your moment now is WL squared over 8. And you end up here with, you can see your dead load moment is 68,300 pounds per foot. Now, for live load, you have a truck loading and a lane loading that you have to use. Now, the truck loading moment of 646, I took out of the AASHTO appendix from the standard specs. They have a listing of all the moments for an HS20 truck. So that's where I got the 646, and you multiply it by 0.31, which gives you the distribution factor of, gives you the load of 200 kip feet from on each girder. And then you also, because LRFD requires that you have to include a lane loading of 640 pounds per lineal foot, and that's WL squared over 8, and so you have an additional 65 kip feet. So now we go back onto our strength 1 design and enter in the dead load and the both live load truck and lane multiplied by the appropriate load factors, and you get 549 kip feet, which is about what you would get on an ordinary highway bridge. Again, we have the same factors here. The only difference is your C sub V, your shape factor is different because now your glue laminated beams are vertical and not horizontal. And so you can see the formula in there for the shape factor. So you still get a nominal resistance of 3340 PSI. When you go back and check the allowable, the actual bearing stress and compare it to the allowable, you can see your bearing stress is 2240 and the allowable is 3340. And you can see, again, we're substantially less. If we were to do this working stress, we would be much closer to the 3000 or the difference between the two would be much closer. Now, one of the things that we also have to do is check deflection. And on timber structures, my experience has been on the short spans, say anything less than about 10 feet, deflection doesn't control. But once we start getting into larger spans, especially in the 50, and I've actually recently did a bridge with a 80-foot span out of a glue laminated beam, it was the deflection criteria that governed. And the deflection criteria for a timber bridge based on AASHTO is L over 500, where you would normally use L over 360 if it was a non-bridge type of structure. Now, the one next thing I want to do is check the shear loads. And you can see your dead load shear from the numbers we had before is 5,355 pounds. Your live load truck, again, we get the 58.5 from the AASHTO appendix from the standard specs multiplied by the distribution factor, and you get 18.1. In the lane load, you get 5.1 kips additional. So that gives you 23.2 kips, and you take all the load combinations here, and you get 41.7 kips is the the shear force at the end of the beam. Now, here the equation for the allowable is slightly different than for flexure, but it has the factor, the increased factor due to converting it from allowable stress to LRFD. It's got the wet service factor and sizing factor and the load duration factor. So your allowable is 265 PSI, and that gets bumped up your nominal strength of 409 PSI in shear. Now, because you're dealing with timber, your shear stress is 1.5 times the actual shear stress divided by the area. And so you can see here you get 163 PSI, which is much less than the 409. So your beam is still good. Here's a picture of the cross section during construction. They'd laid the first span, and you can see these beams. These are the glue laminated beams here. Here's the glue laminated decking. And normally for a timber bridge, we wouldn't put a crown on it. We just essentially just have a flat surface. But this one not only had a vertical curve, but because it was following Florida DOT standards, and because they really didn't understand the the fact that you didn't, that it was a flat, excuse me, that they've never done a timber bridge before. They still required to put a crown on the bridge, which was a little problematic for us because we'd never really put a crown on a bridge. So what we had to do is take the glue lam panels and actually break them, put a break right at the middle, and we actually had to put in a separate glue laminated beam right in the middle just to support the break. Now there will be a wearing deck on top of this, and you can see on the right hand, or excuse me, the left hand side, this metal post, that is the temporary bridge where traffic was going across it. Now these beams, let me tell you, they set these beams up, and we put construction equipment on this bridge, and this bridge did not move at all. Here's a look back at in the other direction. You can see a concrete pier here, a concrete pier here, and then there's the abutment they were just finishing up, pouring up. But you can see the glue laminated beams. These are diaphragms that we put in at the ends of the beams and to help with lateral stability. Like I said earlier, all of this hardware is stainless steel. And again, on the right-hand side here, you can see the single-lane temporary bridge. Here's the crane and working on setting the glue laminated beams in place. And you can see, you get a perspective of how big these beams are. And you would think for a 51-foot span, you wouldn't need that much, but because it's timber and deflection tends to control on timber, you needed a much deeper section. The other thing is that everything had to be barged in. Again, this was an island and there was no bridge to the mainland, so everything either had to be barged in or it had to be ferried across. Now, I want to go through the pedestrian part of it before I get into the railing and stuff. And I'll kind of go over this a little quicker just because it's a lot of repetition, but you have here, what we normally do with these is, this section is a 5-foot walkway. We have a glue laminated beam here on the left and on the right, and then what we have is a load beam going perpendicular to it so that we can put 3x10 stringers, and these load beams are usually about every 7 or 8 feet. So the design parameters for our decking, now on the pedestrian part, we don't really need that much strength, so we're just going to go with 3x8, number 1 yellow pine. The pedestrian loading is 85 pounds per square foot live load, and then the deck span is only spanning 1 foot 10. So you can see your loads are very small. They're 8 pounds per lineal foot for dead load, and live load is 57 pounds per lineal foot because it's only an 8-inch wide plank. And you run through the numbers, and usually, I mean, the planking isn't going to be controlled by live load here. If there's vehicular load on it, which is sometimes what we have to design for, then we end up having problems. Again, you can see what your allowable was, 1500 psi. That's your allowable stress, but your nominal strength goes all the way up to 2650. So when you run the numbers, you can see your decking is 73 psi is the actual flexural stress on the decking, and the decking's more than okay. Now the stringers are spanning, in this case, 6'9", and that's between the load beams, and their stringers are spaced at 1 foot 10. Here we're going to get by with 3x10 Southern Yellow Pine number 2. And again, you run through, you can see that your dead load is 35 pounds per lineal foot, and your uniform load is 156 pounds per lineal foot. You run the numbers with again, the load factors, and you get on this span of almost 7 feet, 1,800 foot-pounds. load factored. Again, you go through your grading and you can see the grading is, the nominal is much less because you're starting out, this was number 2 grade, so therefore your grade, your allowable is only 1050 psi and your nominal ends up being 1480. You run through and do the comparison again and you see that your allowable bending, your actual bending stress is 606 psi, which is much less than the 1480 psi. As we've done before, we looked at the shear load, and at the ends of the stringers, it's 118 pounds dead load, live load's 527. That gives us a factored shear of 1,070 pounds. Going through for grade 2, you start out with your allowable of 175 psi, and when you apply all the factors to it, you end up with 222 psi as the nominal strength. And again, you can see that your stringers are more than adequate. You could have gone to smaller stringers on this and smaller decking, but this is primarily, they have everything pretty well standardized on what they're going to use. And so that's why we picked these sizes. Now, the glue laminated beams are on either side. Again, we have a 51-foot span. The spacing is 2'6", and you can see these are still huge glue laminated beams. They're 6 3/4 inches by 43.5 inch deep. We're going to go through the same thing here, where we have a total load of a dead load of 120 pounds per lineal foot, and your live load is 215 pounds per lineal foot. You calculate out what your dead load and live load moments are, and you end up with a load combination of 171 kip-feet. Your flexural stress is actual is 965 psi, and your allowable is 3380 psi. And again, you go through your dead load shears and live load shears, and you can see that your shear value at the end of these beams is a little under 13,500 pounds. But when you run through and figure out what your allowable is, you can see it's much less. Again, on the pedestrian, we were more concerned about deflection on this. And if I were to run these numbers just using service design, the numbers would have been much closer. The last thing I want to go over before I show you some other pictures is the guardrail design. And this is the most difficult part of a vehicular bridge, is not only designing the guardrail, but it's designing all the connections. You can see, and you'll see the pictures of it in a second, these things are huge. The vehicular posts are 8 3/4 inch by 16 inch glue laminated posts, and the railing element is 10 3/4 by 12 inch posts. And that's bolted through curbing, you can see here, bolted through the curb and the post here, and then the glue laminated beam here with some blocking. This right here was the critical connection, and that's where the decking, the curbing is bolted to the decking because of the edge distances. We design all of our timber bridges for, essentially we're following the standard specs, and that's pretty well what I've done for the past 15 years. And because this was Florida DOT and they required LRFD design, we had to follow the LRFD specs. Now, the standard specs require you to design for an lateral impact load of 10,000 pounds. The LRFD changes depending on the traffic, and you follow Chapter 13 of the LRFD specs, And what we used on this one was a TL2 vehicle and had our posts spaced at 4'6", and we used Southern Yellow Pine 24 F8 posts and rail elements. This is out of AASHTO, out of Chapter 13, and we're pretty well just going to be using the transverse forces here. And these are the different traffic lane type load tests for the railings that are used. And there's actually now a TL7. The TL1 through TL6 that we had here, excuse me, you can see whereas the standard specs use a lateral load of 10,000 pounds or 10 kips, the lowest one here is 13.5. Now, the Florida DOT wanted us to use a TL3, which is 54 kips. And it took us a while to convince them to come down to the 27. The TL3, if you go to the next slide, the TL3 is for a wide range of high arterial highways with very low mixtures of heavy vehicles and favorable traffic sites. They considered this a local road, and they were like, well, we want you to design for a TL3. And we were able to talk them down to a TL2, but we really wanted to get them down to a TL1. You got to remember that this is a bridge over going from one island to another, and you're not going to be going more than 15 miles per hour, maybe 20. The only trucks that are going to be on here are garbage trucks. But they made us design to a TL2, and you can see, if I go back a slide, the force is 27 kips versus what we normally do is 10 kips. So you can see how unrealistic some of this stuff is in designing timber bridges on some of these low volume roads. But because we had to follow the standards, that was what we had to go with. So that's how we ended up with these gargantuan members. Now you can see the railing height is 27 inches, the posts are at 4'6". So designing the railing element, you get a moment of 30 kip feet using the 27 kips and a shear force of 27. And in the post, we're going to apply all of that, applied as a cantilever. So you get 60.8 kip foot and 27 kips as a shear force. Go through the different allowable stresses. Now the other thing is, on this, the duration factor, because it's instantaneous, it goes up to 1. And so everything else, essentially what you end up doing is doubling from the allowable to the ultimate. And you can see the flexural stress goes from the allowable is 4,800 PSI and the actual is 1,550. And we go to check shear, we essentially almost double our shear capacity. And you can see that the nominal is 510 PSI and the actual is 315. So the rail element is good. And when you go through the same check for the posts, and you end up, now you can sit there and see how closely we are for the posts. The allowable is 4,800 PSI and we're at 3,560. And when you go through and check the shear design, you can see we're okay with the shear. So this just gives you an idea of how big in reality these posts were. You can see on there, they're starting to put they've got just laying up some wood here. These are the curb elements that I'm pointing to here. Here's the post, and there's going to be a horizontal element here. One of the things that we had to consider because of the high forces on this is we had to make these things big, not only to take the cantilever load, but to bolt everything together. We had a rail element here, and you had to have enough edge distance to bolt everything together. And the same thing was true when we were bolting the rails to the post to the curb and the decking. A lot of the size of the post had to do with all the connections. And it goes back to the fact that we were using 27,000-pound lateral force. So that gives you an idea of what we had to go through during the design. And these are some of the pictures I took during construction. Now, one interesting thing that came up is this is a picture of the piers. And York Bridge does not do anything in concrete. Everything's in timber. So when it came to doing the concrete design, they leaned on me a lot. And as some of you may know, I spent 25 years in Illinois before I moved out east. But I started doing work about 15 years ago with York, and we would do work all over the country. And I'm used to, okay, concrete design, 4,000 PSI, away you go. And what ended up happening here was we designed the piers for 4,000, and they tested them, and they came out at 5,000. I'm like, oh, everything's good. And so I told them, yeah, go ahead and start setting the beams. Little did I know that the Florida DOT requires 6,000 PSI strength, and that has to do not with necessarily they want high strength, but they want high density because of the salt environment. So now we were 1,000 PSI underneath the strength and had to come up with a solution. And essentially the solution that we came up with was that the tops and sides of these concrete caps have to be coated with a treatment every year, and that's on York to do, because by the time we'd gotten to the point of finding out that the concrete was the wrong strength, we already had placed about half the beams. Again, you can see the stainless steel. The other thing you can see here is the water protection, because we are close to the Gulf of Mexico. Here we're looking at installing the concrete beams here, or excuse me, the timber beams. You can see here's the concrete decking and the timber beams here. You can see again, this is a guy is about 6 foot, a little over 6 foot, and you can see how big these beams are. The hardest part about putting these timber bridges together is these beams are like 2.5 feet apart, but yet they have to bolt everything together. And again, like I said before, everything's stainless steel bolts. And what York does, and pretty much all timber companies that I work with, is we'll put this bridge together. And as everybody knows, timber is going to shrink after time. And so every one of these bridges, they bring somebody back out here a year later and start bolting the hell out of everything and tightening everything up. But you can see the close working conditions that they have here. Well, I hope you enjoyed your the presentation, and just wondering if anybody's got any questions.
So we can give you guys a few minutes if you want to type out any questions, and then after that, if you have any other questions, you can email me or you can email Zeyn with those. But we'll give it maybe a minute or two just in case you guys have any.
Well, I'd like to thank everybody again.
All right, looks like no one has any questions right now. Like I said, feel free to email. Zeyn, I want to thank you for doing this. We really appreciate it. And keep an eye out for January's topic for First Friday. Hopefully we'll be getting that out to you guys shortly. Thanks so much for participating, and we'll see you next month.